Hello, so in this video we will talk about string concatenation and Clean's closure. So let's start with the definition for string concatenation. So let's say we have a vocabulary V and we have set A and B which are subsets of V star. So V star means we have all the strings which can be formed from the vocabulary. Concatenation of A and B denoted by AB is the set of all strings of the form AB such that A belongs to A and B belongs to uppercase B. Okay, and similarly we can define A to the n in a recursive manner. Okay, where A to the 0 is just the empty string. It has only one string, which is the empty string. Remember, lambda is our empty string here. Okay, and we have A to the n is just A to the n minus 1 times A. Okay, so let's see how it works. So let's say we have A is equal to 0 and 1 1 and B is equal to 0 0 and 1 1. We have to find AB. So let's apply the definition. So all the strings whose first element is from A and second element is from B. So first element I can make 0 from A and 0 0 from B. Then 0 from A and 0 1 from B. Then 1 1 from A and 0 0 from B. And then 1 1 from A and 0 1 from B. Okay, so this is my AB. Okay, and now let's try to find B to the 3 here. Okay, so then what? So we have this is equal to B to the 2 times B, and B to the 2 is what? B, not times, B to the 2 B, and this is B, B and B. Okay, so now, so what is let's calculate this one first. So BB, which is what? 0 0 0 1, this is my B, and then concatenate it with 0 0 and 0 1. So this is equal to 0 0 0 0. So first of this and first of this, and the 0 0 concatenated with 0 1 and 0 1 0 0, then 0 1 0 1. So this is my B to the 2. Now B to the 3, this is, now I have to do this with this, or I can do this with this, right? Because the definition says B to the 2 times B. So this one should come first and then this should come second. Okay, so this is 0 0 0 0 and 0 0, then 0 0 0 0, then 0 1. So similarly I can do this with this, and this with this, and this with this, and this with this, and this with this. So I can say last one should be 0 1 0 1 and 0 1. Okay, so this is my B3. Okay, now, so let's say we are given this concatenation here. We have to find all the sets A and B such that AB is equal to this. Okay, so one is just, I mean two are just trivial, right? So one is we have A, this is equal to AB, and B is just the empty string. Second is A is the empty string and B is equal to this AB. Okay, then you note that every string in AB start with 1. So I can say A is equal to 1 and B, this is equal to 0. So I take away 1 from each of the strings and write make B from it. So this is 0 1 0, 0 0 0, 0 1 1 1 and 0 1 0 0 0. Let's say what mode? So I can say A, now 1 0 1 is here and 1 0 1 is here. right? So, and 101 is here. Okay, so I can say 101, and for B I can say 0, 1 1 and 0 0 0. So 0 1 1 and 0 0 0. But this has to match with the other three as well, right? So let's take away 1 from here, and this becomes 0 1 0, make it 1 0, and 1 1 1 is made by 1 and 1 1, and 1 0 0 0 is made by 1 and 3 zeros here. So this also works. These are the four possibilities. If we have this set and we want to create two sets which can be concatenated to form all the strings here, we have these options. So these two are trivial options. So these two are more interesting options. So I would say easy to see that if we have 6 elements here, so the number of elements in A times the number of elements in B should be equal to the number of elements in AB. So I can say cardinality of A times cardinality of B, this is equal to cardinality of AB. Okay. Okay, now we define the definition of the Kleene's closure here. So the Kleene closure of a set A, which is denoted by A star, is that defined by the union of all the powers of A. Okay. Okay, now this is definition is, so I can write it as A union A squared union A to the 3 union A to the 4 union, so and so on and so on. Okay. Now let's see what is the Kleene's closure of this. So what is A squared? A squared is 1 1 0 1 concatenated with 1 1 0 1. So this is equal to 1 1 1 1 1 1 0 1, then 1 0 1 1, then 1 0 1 1 0 1. Okay, so A cubed, this is equal to A squared A. Okay, so this one first and then this. So 1 1 1 1 1 1 0 1, then 1 1 0 1 1, and 1 1 0 1 1 0 1, then 1 0 1 1 1, then 1 0 1 1 1 0 1, then 1 0 1 1 0 1 1, then 1 0 1 1 0 1 1 0 1. Okay, so then, so now what is A star? So by observation, it definitely has 1 1 1 1 1 1 1 1 1 1 and so on, correct? Because of this, then this, then this, and so on. Okay, but what next? So it does have this guy for does it have any other length 2 string or length 3 string? No, but it has some length 4 strings which are 1101 and 1011. Okay, okay. And does it have any length 5 strings? It has one length 5 string, second length 5 string, and I think third length 5 string. Will it have any more length 5 string? No, because this guy and this, the next one should be this 4, and the next rest of them will be at least 6. Okay, so then I will say 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1. Okay, now note that can we generalize it? So this is related to this. Okay, so can we generalize it? Yes, we can generalize it. We can say it has the set of strings starting and ending at 1. Okay, what about zeros? So we saw that for length 5 strings there is only 1 0 in each of them. Okay, so we have 0, we have 0, we have 0, because the starting and ending string should be 1. right? For length 6 string what will happen? So then we will add 1 to each of them, right? We have length 5 here, and then we will add 101 to this guy. Okay, so then we can say each pair of zeros is is separated by at least two ones. Okay, so the Kleene's closure of this set gives us a set of strings which start and end at 1, and for each pair of zeros we have a separation of at least two ones. Okay, so this is not clear at all once we see this, right? But once we do this and we start making, making patterns, we can arrive at this conclusion here. Okay. Okay, now let's say another property of Kleene's closure. The another property of Kleene's closure is that if we have a subset of B, the Kleene's closure of A is also a subset of the Kleene's closure of B. Now, how can we say that? Now, let's say uh, we have A is a subset of B. So let's say we have A, this A1 up to AM, and we have B, which has, because B is a superset of A, so B is A1 up to AM, and let's say it has, let's say, just one more element. Okay, you can generalize it with more elements, but this serves our purpose. Okay, so what is A squared? So A squared will be A1 A1, and then AM A1, and then A1 A2, and then AM A2, and so on up to AM AM. What's B squared? B squared is also the same, except some more element. We have A1 A1 up to AM A1, and then we have another one, B1 A1, and then in the end we will have AM AM, then we have B1 AM, and then in the end we will also have B1 B1. Okay, so then we can say A squared is a subset of B squared. Now similarly we can say any uh, power of A, so to speak, is a subset of B to the K. So this means A union A1 union up to so on, or let's say A squared union. This is a subset of B union B to the B to the 2, B to the 3, B to the 2 here, B to the 3 here, and so on. This means that the Kleene's closure of A is a subset of the Kleene's closure of B. Okay. So this is, as a recap, we defined string concatenation, which was a very basic, I think the concept comes very naturally, and we defined the Kleene's closure. Okay. So, but the trick here is, I think the more involved procedure is how to find a Kleene's closure of a set and how to make a general statement about that Kleene's closure. Because forming this Kleene's closure of this set was easy, but to come up with the decision that it represents this kind of rules is the challenge here. Okay. Okay. So this is it for this video. Hope it was easy to understand. Thanks for watching and hope you liked the video.